There are monsters out in the cosmos that can swallow entire stars, that can destroy space itself. Black holes. For decades, they remained completely hidden. But now, scientists are venturing into their uncharted territory. They've discovered that black holes don't just rule the realm of stars and galaxies. They impact all of us here on Earth. Because black holes just might be the key to understanding the true nature of reality. Space, time, life itself. The secrets of the cosmos lie through the wormhole. Take planet Earth and squeeze it down to the size of a marble. You'll create an object so dense that not even light, traveling at 186,000 miles per second, can escape its extraordinary gravitational pull. Its name? A black hole. Astrophysicists think that black holes might form when giant stars run out of fuel and collapse under their own weight. We're not really sure. Why? Because black holes are places where the accepted laws of physics break down. A few bold thinkers are now making giant strides towards understanding what goes on inside black holes. And the new laws of physics that emerge have an astonishing implication. You, me, and the world we live in may be nothing more than an illusion. In my hometown in Mississippi, there was a well. It fascinated me to gaze into its murky depths to try and see what lay at the bottom. I would sit there, throwing pebbles into it, trying desperately to hear a faint splash of water. But all I got was silence. One day, I took a dime-store toy soldier, made a parachute for it out of an old handkerchief, and watched it float down. I wondered what would happen to him when he hit the bottom, or if he would just keep on falling forever into that impenetrable blackness. Today, theoretical physicists are drawn to black holes like I was to that old well, trying to understand how they really work and what they can tell us about the universe.
It's one of those things that sounds like science fiction, only it's better because, it's real.
A black hole is the window into a world that we don't have the concepts. We don't even have the mental architecture yet to be able to envision properly.
You're in this strange world of strong gravity where there are no straight lines anymore.
You can't even see it. That is disturbing and exciting at the same time.
The notion of a black hole is a natural extension of the laws of gravity. The closer you are to a massive object, the more the pull of its gravity slows down anything trying to escape from it. The surface of the Earth is 4,000 miles away from its center, so the force of gravity up here is not very strong. Even a kid can resist it, for a second or two. But if you could squeeze the Earth down so that all of its mass is really close to the center, the force of gravity would grow incredibly strong. Nothing could move fast enough to leave its surface. Not just a jumping boy. Even the beams of light speeding out from his shoes would be trapped.
So if you're trying to imagine creating something so dense that not even light can escape, you're trying to get a system so compact that the speed that it takes to escape from that object is greater than the speed of light. Now the speed of light is 186,000 miles per second, so that's going really fast. Gravity is quite weak. I think it's surprising. The whole Earth is pulling on a rocket ship, and all it has to do is go 7 miles per second to escape from the Earth. And to get all the way to a black hole, you'd have to crunch down the entire sun to be less than a few kilometers across. Now it would take something traveling greater than the speed of light to escape, so nothing can escape, and the whole object goes dark.
Christian Ott, an astrophysicist at the California Institute of Technology, has been trying to understand how such strange entities as black holes might really form in the cosmos. He studies what goes on when giant stars run out of fuel and start to shrink. A process comparable to the collapse of an exhausted marathon runner.
So sometimes you can compare a star at the prime of its life with a runner who's just starting out, still real fresh, consuming oxygen aerobically. And it's the same with stars. They burn hydrogen into helium slowly, and they're getting a lot of energy out of every single hydrogen nucleus they burn. After they're done fusing hydrogen into helium, they go on to more and more heavy elements, and that fuel goes fast and fast. So at the end, they end up with iron, and that's when their fuel is over, fuel is out. And it's basically like a marathon runner hitting a wall in a marathon.
But unlike a runner who can restore his energy with food and drink, a dying star has no way to come back from the brink.
There's no more heat generation, no more energy generation happening at its core. So gravity keeps on pulling in, and since there's nothing producing pressure to sustain it, it will just collapse. You get a shock wave, and the shock wave moves out, and it actually blows up the entire star, and that's the phenomenon we call supernova.
The death throes of giant stars are the most dramatic events astronomers have ever witnessed. Chinese stargazers saw one explode in 1054. It was so bright, they could even watch it by day. Another two blew up around 400 years ago. These colossal explosions leave debris fields of gas and dust hundreds of light years across, still visible and still expanding today. But what interests black hole researchers is not the explosion. It's what happens at the very center of the dying star. Modern astronomers have never witnessed a star in our own galaxy explode. But theoretical physics predicts that if a star is large enough, its collapsing core should shrink down to form a black hole.
So imagine the balloon is the star, and the star stays alive by burning thermonuclear fuel, and as it does so, you get heavier elements like the sponge, and all that energy released, like the energy released in a bomb. So as the star runs out of fuel, it begins to cool, and as it cools, it's no longer supported by all that pressure, and so it starts to collapse under its own weight, and it will continue to collapse until it gets so small that now you're running up against the pressure of crushing the matter together. And at this stage, it's a little bigger than the size of the Earth, and it's supported by pushing all of the electrons in the atoms closer and closer together. Now, if it's more massive than a couple of times the mass of the Sun, it will start to collapse even further. And there is no form of pressure that can resist this collapse, and it will continue to collapse down until it forms a black hole.
But do such strange crushed corpses of stars really exist out in the cosmos? Could they be lurking at the center of some of those clouds of gas and dust thrown off in a supernova? Christian Ott and his theoretical astrophysicist group at Caltech are trying to discover whether exploding stars really do form black holes.
Well, I'm just generally, I'm really excited about stars that blow up, actually. First of all, to get a black hole, you need low specific angular momentum. To have a critically spinning black hole, you need a lot of angular momentum. So
There are two ways to find out whether black holes really form when stars blow up. One is to wait for a supernova to go off in our galaxy and use every tool of modern astronomy to pick it apart.
A galactic supernova would provide us so much information we wouldn't sleep for weeks. But unfortunately, it happens only maybe once or twice per century.
So Christian and his team are trying a different approach, blowing up stars inside powerful supercomputers. This is no easy task. In fact, no one has pulled it off. But Christian is on his way to being the first.
So simulating supernovae, stellar collapse, and black hole formation is so hard because it brings together a lot of physics. It's general relativity for gravity, it's fluid dynamics for the gas that collapses, it's particle physics. Doing these simulations is like trying to do a really good weather forecast.
So far, Christian has failed to make a virtual star explode in a way that looks like a real supernova. But after years of refining the physics and the math, he now thinks he may be the first to fully understand how a black hole is born.
Yeah, that is a event horizon right there.
Yeah, nice black hole in the center.
Wow, that's the first time that we do see this.
What's surprising is that the most promising simulations don't actually explode. They simply collapse. It's not a bang, but a whimper. Its name, not supernova, but unnova.
It's basically just everything eventually sinks into a black hole, and the star slowly but surely just disappears. It could be true that most stars, or a large fraction of stars, just disappear. We don't have any data on that. We have never seen an unnova.
If Christian is right and black holes form silently, then these cosmic cannibals could be hidden in plain sight all around us, and we might never know it.
Finding black holes is terribly, terribly difficult. Even if it wasn't black and would be radiating energy, it would still be only, let's say, 20 miles across. And even, at 10 light years away, it would be impossible to find, even with the best telescopes we have.
But if black holes are almost completely elusive, no one told this man. He spent the past 30 years hunting one, a giant one, right at the heart of our own Milky Way galaxy. And his discovery will overturn all our ideas about how the universe really works. In 1931, a Bell telephone researcher, Karl Jansky, was testing a new system for sending radio messages across the Atlantic to Europe. He was plagued by background noise. After 2 years of careful work, Jansky stripped out most of the interference. But one strange signal never went away. It was loudest whenever his antenna was pointed at the constellation Sagittarius, at the very heart of the Milky Way. It was a signal unlike anything a star would make. Astronomers began to wonder whether it might come from an object theorists had predicted, but never detected. A black hole. But there was no way to find out. The center of our galaxy is hidden from view by a thick veil of dust. Then, 25 years ago, a German astronomer, Reinhard Genzel, found a way to see through the fog.
The problem is, we are sitting in the Milky Way, and the galactic center is sort of just along the way through the entire plane of this big spiral galaxy we're sitting in. And there's all this gunk, this dust and this gas between us and the galactic centers. You can't see it in the visible. But at longer wavelengths, this dust is not as efficient.
Infrared light with its longer wavelength is perfect for penetrating the veil, but it's terrible at getting through the water vapor in Earth's atmosphere. So Reinhard Genzel headed for the highest, driest place on Earth, the Atacama Desert of Chile. Beginning in 1992, he and his team at the Max Planck Institute began what would become an enduring campaign to find out exactly what was causing the strange noise at the center of the Milky Way.
In fact, we found in the center of the Milky Way a very dense collection of stars. That's the very center of the Milky Way around which everything turns. And then came the first suspicions. Maybe there's something there.
Reinhardt had a hunch that a black hole could be acting as a colossal center of gravity, causing dozens of stars to whirl around it. So he settled in for the long haul. Each year he took another set of pictures, plotting the movement of that cluster of stars at our galaxy's heart. He gathered a large team to help him handle the immense amounts of data, and used a new technique called adaptive optics to make the images of these distant stars sharper.
So if you look at what the galactic center would look like in a normal telescope, let's say, you would get images which look like that. The effect of this adaptive optics you can see on the right-hand side. It's just amazing how beautiful that image gets. It's really the same scenery. You can recognize those two stars here on the left-hand side. In the blurred image, they are these two stars on the right-hand side.
As the years went by, a striking pattern emerged. Stars were moving really fast. This was something that no astronomer had ever seen before. A dozen, then 20, then 30 stars, all swirling at breakneck speed around a central object that was completely dark and tremendously dense. Could this be the first proof that black holes existed? And if so, was there really one here, right in the center of our own galaxy?
What do you do in order to see something or prove the existence of something which you can't really see, right? And the black hole, you would think, is something, well, by definition, light can't escape from. But you have gravity. Think of the solar system, okay? You have the sun in the center, and then you have the planets. The outer planets move very slowly around the sun. And the closer you come to the sun, the faster the planets go. So suppose in your mind you switch off the sun, you would have to conclude that there's a central object with one solar mass around which the planets orbit. See, that's what we're doing. So these are the stars of the show. Here at the very center here is the radio source, which we suspect is the location of the black hole. This is our best star, which we have followed for 15 years to trace a full orbit.
This star, known only by the name S2, was moving at a phenomenal rate. At its closest approach to the dark central object, Reinhardt and his team clocked it moving at 11 million miles per hour.
What we learned from this is that indeed there's only one central mass right there at the position of the radio source, and that has 4 million solar masses. There cannot really be any believable configuration which we know of other than a black hole.
Reinhard Genzel had made the first definitive discovery of a black hole. But more than that, His team had found an object that must have swallowed millions of stars over its lifetime. Astronomers call it a supermassive black hole. But despite the enormity of this discovery, it would be just the first of many increasingly bizarre and disturbing findings. The next was to figure out what goes on inside a black hole. What happens to stars, planets, even people if they get too close to this cosmic sinkhole? No telescope can ever see inside black holes. To understand how they twist reality, we have to stop looking and learn how to listen. Lurking at the center of our galaxy is an object that's completely invisible, but weighs as much as 4 million stars. Astronomers now believe almost every galaxy has a supermassive black hole at its core. So, what are they? Science fiction sees black holes as cosmic time machines or portals to a parallel universe. But real scientists are finding that truth is stranger than sci-fi. You're about to enter a world where the very big and the very small are indistinguishable, where reality and illusion are one and the same. Astronomer Julie Comerford has been studying the centers of dozens of distant galaxies, trying to find signs of black holes, hoping to learn more about these mind-bending objects.
It turns out that in all or nearly all galaxies, wherever we look, they have a central supermassive black hole at their heart. Supermassive ones are the ones that have masses of anywhere from 1 million to 1 billion times the mass of the sun. You can see a supermassive black hole when gas is falling onto it, and sort of right before the gas falls into it, it gets heated up and emits a lot of energy and can appear really bright.
But when Julie investigates the glowing gas surrounding these giant black holes, she finds something totally unexpected. There's a cosmic dance going on a scale that's almost unimaginable.
You saw 2 peaks in the light instead of just one. You'd expect one from one black hole that's just sitting at rest in its galaxy, but we saw 2 peaks with different velocities, and that immediately hit us as this has got to be something interesting.
Julie began thinking about what would happen when 2 galaxies collide. And if both had black holes at their centers, what would happen to those massive objects?
So when 2 galaxies collide, the black holes at their center, instead of crashing in head-on, they begin this swirl or dance. And the way that we can detect these waltzing black holes is by looking at the light that's emitted from them. So for the black hole that's moving towards us, we detect light that is at smaller wavelengths scrunched up together, so we see bluer light. And for the black hole that's moving away from us, we see stretched out longer wavelength light that appears redder. So it's this redder and bluer light that is a telltale signature of a black hole waltz. Every time we see it, we high-five in the observation room, and we just can't get over it.
As Julie scans the universe, she finds the same remarkable dance happening time and time again. In galaxy after galaxy, black holes are paired up and dancing the cosmic night away.
So we identified 90 galaxies from when the universe was half its present age, and we found that fully 32 of them, or about a third, had black holes that exhibited this blue and red signature. So that was really surprising that such a high fraction of the black holes were not stationary at the center of the galaxy at all, that they were undergoing this waltz with another black hole.
Scientists like Janna Levin believe the discovery of waltzing black holes opens up a whole new way to learn what's inside them, because their dance might not only be visible, it could also be audible. The scientific visionary Albert Einstein saw space and time as a flexible material that could be distorted by gravity. A black hole is merely a very deep well in this material. When 2 black holes come close to one another, these 2 orbiting wells stir up space-time and send out ripples that can travel clear across the universe.
And these waves will move out through the universe, traveling at the speed of light. So we can hope to not see black holes with light, but maybe in some sense hear them if we can pick up the wobbling of the fabric of space-time itself.
For the past several years, Janna and her colleagues have been trying to predict the sounds black holes make as they spin around one another. The calculations are not for the faint of heart. Modeling what happens when 2 giant objects create a storm in the sea of space-time takes some serious math and months of supercomputing.
This is the orbit of a small black hole around a bigger black hole, and it's literally making a knocking sound on the drum, where the drum is space-time itself. Well, it really sounds like a knocking. It starts to get a higher frequency and happen faster until it falls into the big black hole and goes down the throat. And then the 2 will ring out together and form one black hole at the end of the day. Then it just sort of, chirps up.
Because black holes stir up the space and time around them so much, the orbit of one black hole around another looks nothing like the orbit of Earth around the sun.
An orbit can come in around a black hole and do an entire circle as it loops around before it moves out again. So instead of getting an oval, you get a three-leaf clover that processes around.
This clover leaf pattern keeps coming out of the simulations. Jana was shocked because this picture of how two of the heaviest objects in the universe move around one another bears an uncanny resemblance to the way two of the lightest objects move around one another, the tiny protons and electrons inside an atom.
We can build a kind of classical atom out of a big black hole, like a nucleus, and a light black hole, which acts like an electron. And together they form a real atom in a sense.
How could an object that weighs so much behave like a subatomic particle that weighs so little?
When we talk about ordinary objects or people even, they are never exactly the same. I mean, you could try to clone me and still the different copies of me would not be exactly the same. And in that sense, people and ordinary objects are not like fundamental particles. They're distinguishable. But the black hole is quite different from that. Black holes are like fundamental particles, and that's very surprising because they're huge macroscopic objects.
Right now, this idea is only a tantalizing hunch. But in just 5 years, supersensitive detectors should be able to pick up the ripples in space created by two massive black holes spinning around one another. And they'll tell us whether they really do behave like tiny atoms. But this connection between the very big and the very small has already sparked a war between two of the greatest living physicists. One of them, Stephen Hawking. The other began life as a plumber in the South Bronx and is now using black holes to develop the most revolutionary idea in physics since Albert Einstein, an idea that literally turns reality inside out. Black holes are the most massive objects in the universe. Some weigh as much as 1 billion times more than our sun, but no one really knows how big they are. All that mass could fit into a space smaller than an atom. And that's where physics runs off the rails. Albert Einstein's theory of relativity explains gravity beautifully, but it only works for very large objects, not for tiny building blocks of matter like atoms.
We understand so much since Einstein, but somehow gravity stands apart from our understanding of everything else in nature. There's matter on one side, and there's gravity on the other side. And there's this great ambition to put those two together, to understand them as one law of physics.
The first step in joining the physics of the very large and the very small came in 1974 from the mind of Stephen Hawking. The theory of the very small, quantum mechanics, predicts that empty space should be sizzling with particles and antiparticles, popping into existence in pairs and then annihilating one another an instant later. These particles exist for such a short time, they are not considered part of reality. Physicists call them virtual particles. But Hawking realized there was one special place in the universe where these particles could become real. Around a black hole, there's an invisible line in space called the event horizon. Outside that line, the hole's gravity is just too weak to trap light. Inside it, nothing can escape its pull. If a pair of virtual particles formed just outside the event horizon, then one of the pair might travel across that point of no return before being able to recombine, falling into the black hole and leaving its partner to escape as real radiation, Hawking radiation. If Hawking is right, black holes should not actually be black. They should shine, ever so faintly. No one has ever detected Hawking radiation from the rim of a black hole. In fact, it's so faint and black holes are so far away that it will probably never be possible. But Jeff Steinhauer thinks he's found a way to test Hawking's theory and send shockwaves through the world of physics. He's the only person on the planet who has seen a black hole from up close. In fact, he's learned how to create one.
My black hole is in no way dangerous. It's a sonic black hole. It can only absorb sound waves. It's only made of 100,000 atoms, which is very little matter. And I'm sure that my neighbors would love that I would put a sonic black hole around my apartment, but it's not going to happen.
When he's not jamming in the basement of the physics department at the Technion in Israel, he's upstairs in his lab. Jeff Steinhauer's recipe for making a sonic black hole begins with a tiny sample of rubidium atoms, chilled down to minus 459 degrees Fahrenheit.
While I was working with these very cold atoms, I stumbled across a phenomenon when the atoms are actually flowing faster than the speed of sound, then if there are sound waves trying to travel against the flow, they can't go forward. And this is analogous to a real black hole where light waves cannot escape due to the strong gravitation.
Even though this black hole traps only sound, not light, the same laws of quantum mechanics apply to it as they do to its cosmic cousins. If Hawking's theory about black holes is correct, Jeff should be able to detect tiny sound waves escaping.
There should be pairs of sound waves, one on the right side and one on the left side. Due to the quantum physics, they will suddenly be created. This is the elusive Hawking radiation.
Jeff has not detected this elusive radiation yet, but he believes he should within a year as he refines his experiment. No one will await that news more keenly than Leonard Susskind. He has spent much of the last 30 years thinking about Hawking radiation and being deeply troubled by what it means. Today, he's one of the world's leading theoretical physicists, but that's not the way he started.
When I was 16 years old, I was a plumber, fixing toilets and sewers and so forth in tenement buildings in the South Bronx was not what I wanted to be doing for the rest of my life. Whenever I make analogies about physics, it always seems that they have something to do with plumbing. The analogy that I've used over and over about black holes is water going down a drain. The invention of string theory, which has a lot to do with tubes. Some people even say this must have been Susskind the plumber.
Leonard Susskind's fascination with black holes began 30 years ago when he listened to a talk by Stephen Hawking, a talk that triggered a violent reaction.
I first heard Stephen Hawking give a lecture up in San Francisco in which he made this extraordinary claim that black holes seem to violate the very, very fundamental principle of physics called conservation of information.
7 years after his groundbreaking work on black hole radiation, Hawking had taken the idea to its logical conclusion. For every ounce of material a black hole absorbed into its core, it would radiate away an equivalent amount of energy from its event horizon. But since there is no physical link between the center of a black hole and its event horizon, the two processes could not share any information.
Now, this was a disaster from the point of view of the basic principles of physics. The basic principles of physics say that you can't lose information. Let me give you an example. Here's a sink of water. We imagine sending in a message into that sink of water in the form of Morse code by dropping in this red ink. Drip, 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 drop, drip. You see the red ink swirling around, but if you wait a few hours, what will happen is that red ink will get diffused throughout the water. You might say, well, my goodness, the information is clearly lost. Nobody can reconstruct it now. But down at the very core of physical principles, no, that information is there. If you could watch every single molecule, you could reconstruct that message. It may be much too hard for human beings to be able to reconstruct and to follow all those motions, but physics says it's there.
But Stephen Hawking claimed there are special places in the universe where that law can be broken.
What happens when the information goes down the black hole? The answer, according to Stephen, was it goes down the drain and disappears completely from our universe. This was a fundamental violation of the most sacred principle of physics, and I was personally truly shocked.
If what Hawking claimed was right, it would mean most of modern physics had to be seriously flawed. Black holes would spend their lives eating stars and leave no record of what they'd done. Nothing else in the universe does this. The fiery blast of a nuclear bomb might vaporize everything in sight, but all that information is still in this universe, no matter how scrambled. Black holes, according to Hawking, don't scramble information. They completely destroy it.
That was 1981, and from that time forward, I was hooked. I could not let go of the question of black holes.
This squabble soon grows beyond these two men and engulfs all of physics. At stake is more than just bragging rights for the winner. It turns out to affect the very way we perceive the universe. There may be 100 million black holes scattered across the Milky Way. Anything that strays too close to these dark remnants of burned out stars will be pulled in by an intense gravitational field. But what actually happens to the stuff that falls into a black hole? Is it simply wiped out of existence? Or do black holes remember? These are the battle lines of the Black Hole War. A battle with repercussions that the men who started it could never have imagined. It's a war between two giant minds. On one side, the famous physicist Stephen Hawking. On the other, Leonard Susskind, one of the creators of string theory, a notoriously difficult branch of physics. Stephen Hawking argues black holes destroy what they swallow without a trace. Leonard Susskind passionately disagrees. But for 10 years, he struggled to find anything wrong with Hawking's concept of how black holes radiate away the matter they swallow.
It was thought to be inconceivable that somehow the things which fell into the black hole could have anything to do with the Hawking radiation, which was coming out from very, very far from where the particles fell in.
Then he began looking at the problem in a new way. Call it the dead and alive paradox. It's a cosmic thought experiment starring an astronaut named Alice, her friend Bob, and a black hole.
Bob is orbiting the black hole in a spaceship, and Alice decides to jump into the black hole. What does Bob see, and what does Alice see? Well, Bob sees Alice falling toward the black hole, getting closer and closer to the horizon, but slowing down.
Because the gravity of the black hole severely distorts space and time near the event horizon, Einstein's theory of relativity predicts that Bob will see Alice moving slower and slower until she eventually stops.
So, from Bob's point of view, Alice simply becomes completely immobile with a big smile on her face, and that's the end of the story. It takes forever for Alice to fall through the black hole. On the other hand, Alice has a completely different description of what happens. She just falls completely cleanly through the horizon, feeling no pain, no bump. It's only when she approaches the interior when she starts to feel uncomfortable. At that point, she starts to get more and more distorted, and I don't want to go into in detail what happens to her. It's not pretty.
These two descriptions of the same events appear to be at odds. In one, Alice is stuck at the event horizon. In the other, she sails right through. In one version, she dies. In the other, she's frozen in time, but alive. But then, Leonard Susskind suddenly realized how to resolve this paradox and win the black hole war.
I began to think that some of the ideas that we had developed for string theory could help resolve this problem, this paradox. One way of thinking about string theory is that elementary particles are simply more than meets the eye. You see this propeller here? This propeller, when it's spinning very, very rapidly, all you see is the central hub. It looks like no more than a simple particle, but if you had a really high-speed camera that could catch it as it was spinning, you would discover that there's more to it than you realized. There's the blades, and the blades would make it look bigger. In string theory, an elementary particle has vibrations on top of vibrations. It's as though this propeller had on the ends of its blades more propellers, and those propellers had propellers on the ends of their blades, out to infinity. Each propeller going faster than the previous one. As you would catch it with a higher and higher speed camera, you would see more and more structure come into focus. And the particle would seem to grow. It would grow endlessly until it filled up the whole universe.
Leonard realized that a black hole is like an ultra-high-speed camera. It appears to slow objects down as they approach the event horizon. Time for another thought experiment. The black hole, Bob, and Alice are back. But this time, Alice has an airplane powered by a string theory propeller. For Alice, not much changes. She sits in the cockpit and flies right over the event horizon, all the time seeing just the central hub of her propeller. And she meets the same horrible fate at the heart of the black hole, this time accompanied by some plane debris. Bob's view is very different.
So first he sees the first propeller come into existence. Then later, when it's slowed down even further, he begins to see the outer propellers come into existence, sort of one by one, and the effect is for the whole propeller to get bigger and bigger and bigger and grow and eventually be big enough to cover the whole horizon.
These two views no longer seem so irreconcilable. Alice is either squished at the center of the black hole or smeared all over the event horizon. Leonard has a name for this new way of seeing things, the holographic principle.
I began to think, hey, wait a minute, this sounds awfully much like a hologram. There's Alice at the center, and if I look at the let me not call it the horizon, let me just call it the surface, the film, all you see is a completely scrambled mess, and somehow they're representing exactly the same thing.
Leonard's idea that the event horizon of a black hole is a two-dimensional representation of a three-dimensional object at its center solves the problem of information loss. Every object that falls into a black hole leaves its mark both at the central mass and on the shimmering hologram at the event horizon. When the black hole emits Hawking radiation from the horizon, that radiation is connected to the stuff that fell in. Information is not lost. In 2004, at a scientific conference in Dublin, Hawking conceded defeat. Black holes do not destroy information. Leonard Susskind had won the black hole war. But he'd done much more than that, because the theory does not merely apply to black holes. It forces us to picture all of reality in a new way.
It's as if there were two versions of the description of you and me and what's in this room, one of them being the normal perceived three-dimensional reality, and the other being a kind of holographic image on the walls of the room, completely scrambled, but still with the same exact information in it. That idea has now, it's not an idea anymore, it's a really basic principle of physics, that information is stored on a kind of holographic film at the edges of the universe.
In a sense, three-dimensional space is just one version of reality. The other version exists on a flat holographic film billions of light years away at the edge of the cosmos. Why these two realities seem to coexist is now the biggest puzzle physics needs to solve.
One of the big challenges that comes out of all of this is understanding space itself. Why is space three-dimensional when all of the information that's stored in that space is stored as a two-dimensional hologram? A black hole raises these challenges and really sharpens these challenges because it's practically a place where ordinary space doesn't exist anymore. So if I'm asked questions about how space emerges, I will simply have to say, well, we're thinking about it. We don't understand it.
Black holes have been a source of fascination for almost a century. We've thought of them as time machines, shortcuts to parallel universes, as monsters that will one day devour the Earth. Well, any of these ideas may turn out to be true one day, but right here, right now, black holes have a profound effect on you and me. Their shimmering holographic surfaces seem to be telling us that everything we think is here is mirrored out there, at the very edge of our mysterious universe.